we are going to start with the topic of increasing the capacity of parallel plate capacitor. So we will learn how we can further increase the capacity of parallel plate capacitor. But before starting with this topic, I will be telling you about the dielectrics. So we are starting with dielectric. See, dielectrics are insulators, or in other words we can say these are electrical insulators. That means these materials cannot conduct electricity, but at the same time when these materials are kept in electric field they gets polarized. So overall we can say dielectrics are insulators which can get polarized when they are kept in electric field. So we will be studying how we can use these dielectrics to increase the capacity of parallel plate conductors. So firstly, we will be understanding the electric fields produced in these dielectrics. Now let us suppose we have a parallel plate capacitor and let us place a dielectric plate or a dielectric slab inside the separation between two plates of parallel plate capacitor. So this is a dielectric and thickness of this dielectric slab is T, whereas the total separation between two plates of parallel plate capacitor is D. So here we are taking D is greater than T. So now we will be understanding the electric fields. Now we know the electric field between two plates of parallel plate conductors or parallel plate capacitor is from positive plate to negative plate. So electric field will be from positive plate to negative plate. Now let this electric field is E naught. We are representing this electric field between two plates as E naught. Or we can say when we are not placing any dielectric material between these two plates, electric field was E naught. So original electric field without any dielectric material inside is E naught. But then we are placing a dielectric slab between these two plates. So what will happen when we place this dielectric slab? Due to positive charge on plate a negative charge will be induced on one side of this dielectric slab, and at the same time due to negative charge on plate B, a positive charge will be induced on other side of dielectric slab. But we must keep one thing in mind, that this negative charge induced on one side of dielectric slab will be lesser than the positive charge on plate A. Similarly, positive charge induced on other side of the dielectric slab will also be lesser than negative charge on B, because basically the slab kept in between these two plates is an electrical insulator. It will not have much negative or positive free charges. So of course it will get polarized, but the surface charge densities on slab will be lesser than surface charge density on the outer two plates of parallel plate capacitor. So we will be moving further. So I will be redrawing this diagram so that we can move further with the derivation. So we have two plates of parallel plate capacitor, and electric field between two plates is E naught. And now we are placing a dielectric slab of thickness T between these two plates, and surface charge gets induced in this dielectric slab. Now, when this surface charge get induced, there will be some electric field produced in this dielectric field. Let this dielectric material has electric field ED. This is produced due to charges induced on its surfaces. Now E naught is original electric field, ED is field induced inside the dielectric. Here ED will be lesser than E naught. Why? Because sigma or surface charge density on parallel plate capacitor is greater than the charges present inside the dielectric slab. We have done it earlier also. So E naught will be greater than ED. Therefore, the net electric field inside the dielectric slab will be equals to E naught minus ED, because E naught and ED are in opposite direction. Now let these two values, E naught and ED, their subtraction is equal to E. Let the net electric field inside the dielectric slab is E. Now this E will be equals to E naught minus ED. So this is the point that we need to keep in our mind before proceeding. Next, let us start the derivation. Now we will be deriving the expression of capacity of parallel plate capacitor when dielectric slab is kept. D is the separation between two plates and T is thickness of the slab, dielectric slab that we are keeping. So to calculate capacity, firstly we will have to find the total potential between the plates. So total potential between plates will be equals to, we will be denoting this with capital V, and this will be equals to, total potential will be equals to potential in the free space, plus potential in dielectric slab. So our total potential will be equals to the sum of potential in free space and potential in the dielectric slab. So now we just need to write the expressions of these. Now the total potential will be equals to Now we know the formula for electric potential is equal to electric field multiplied by separation. So now the potential in the free space will be equals to electric field in the free space. We have taken it equal to E naught multiplied by the free space between two plates. Now free space will be equals to D minus T because T is the thickness of that slab plus electric field in the dielectric. Now electric field in the dielectric we have already calculated it. It was equal to E and that we have calculated as E naught minus ED. So we will be writing it as E, net electric field inside the dielectric slab. This net electric field inside the dielectric slab will be in direction of original electric field, that is E naught. So this electric field will be in direction of E naught. That is why we are adding these two. Multiply by separation. Now this electric field E exists in the thickness T. So we will be writing it as E into T. So now further we know that what is dielectric constant. When we are keeping some dielectric inside two plates, we must know the value of dielectric constant. Now what is dielectric constant? Dielectric constant, it is denoted by K, and dielectric constant is equal to electric field in air or vacuum divided by electric field in some medium. So this ratio is called dielectric constant. Therefore, we can easily say electric field in any medium will be equals to electric field in air divided by dielectric constant. In our case, we can write E is equal to E naught by K. So we will be using this expression over here to proceed further. So you must write these down. So we will be writing the above expression as V is equal to E naught D minus T plus, instead of E we will be writing E naught by K, where K is dielectric constant, into T. So this is what we will get. Now further we can take E naught common and we will be left with D minus T plus T by K. So this is the value of net potential between two plates of parallel plate capacitor. Next we will be calculating the capacitance. We know capacitance is equal to, we have already done it number of times, capacitance is equal to, it is the ratio of electric potential and charge. So we will be writing it as C is equal to Q over electric potential. We know Q is equal to CV is the popular formula. So C is equal to Q over V. Now what is V? V is E naught D minus T plus T by K. So this is the value of capacitance. Further, we can write electric field in between two plates. We know electric field between two plates is equal to sigma over epsilon naught. So we can replace, and at the same time sigma can be written equal to charge upon area. So electric field can be written equal to Q over A epsilon naught. So we can replace E naught by Q over A epsilon naught. Rest will remain same. Next, this Q and Q will get cancelled out, and we will be left with epsilon naught A over d minus t plus t by k. So this is the expression for capacitance of parallel plate capacitor when a dielectric slab is kept between the two plates. Next we will be doing a special case. You must remember this equation, this formula. It will be used in number of numericals. Next we will be doing a special case, that what will happen if entire space between plates is filled by dielectric. If dielectric is filling the entire space, that means earlier what we did, we took a dielectric slab of thickness T. Now if instead of thickness T, the dielectric slab has thickness D, then what will happen? So our capacitance now will become, capacitance as we have already written it as epsilon naught A over D minus T plus T by K. Now in this case T will become equal to D. So what will happen? These two will get cancelled, and instead of T we can write D. So our expression will become C is equal to epsilon naught A over D, and this K will go up. So our expression will become epsilon naught K A over D. So this is the expression which we will get. So capacitance of parallel plate capacitor when dielectric is placed is equal to K epsilon naught A by D. So now if you look back, we proved that capacitance of parallel plate capacitor is equal to epsilon naught A by D when nothing was kept in between the two plates. But now what we got is epsilon naught A by D into K. So if we substitute this value over there, we will get CD, capacitance with dielectric slab, is equal to K into C. This proves that capacity of dielectric when it is placed between plates of parallel plate capacitor will increase. So capacity of parallel plate capacitor with dielectric is greater than capacity without dielectric. So from here the things are quite clear. So next we will be doing case number 2. Now if instead of dielectric slab, if we place a conducting plate or a conducting slab, what will happen? Instead of placing that insulating slab, if we kept a conducting slab, what will happen? Now let this slab is a conducting slab. Now one thing you must keep in your mind, that for conductors dielectric constant is equal to infinite for conductors. Now for conductors, when K is equal to infinite, our formula, we will be writing capacitance with conductors Cc. Now this will become equal to epsilon naught A into K. Now what is K? K is infinite. So all our value, it will become equal to infinite. Therefore capacity will become infinite. Now the question is, what does this mean? Infinite capacity of parallel plate capacitor when conducting slab is kept. What does this signifies? So we'll be understanding this. Now, when two plates, the space between two plates, when it is filled with conducting slab, it simply means that now charge will move from positive, it will go to plate A, and the separation between A and B is filled by a conducting material. So this charge will simply move from A to B. This means this entire circuit will be a continuous electric circuit. So you can give infinite amount of positive charge to plate A because the charge is moving from A point to B point. So there is nothing about storing the charge. The charge is just moving from one point to another point. So this does not mean that it has greater storing capacity. Although you can give infinite amount of positive charge to plate A, but at the same time you must understand the charges are not getting stored. This entire circuit is just acting like a conducting wire. So we can say we can give infinite amount of charge to plate A, but at the same time this entire circuit is working as a conducting or as working as a electric circuit, a continuous electric circuit. So we will not be using this conductor material to increase the capacity. Although capacity becomes infinite, but the storing of charge is not actually taking place. It is just working as a continuous electric circuit. So we will be using all these formulas and concepts to solve the numericals. I am again writing the formulas. Capacity of parallel plate capacitor is equal to epsilon naught A by D when nothing is kept between two plates, and this capacity is equal to K epsilon naught A by D when a dielectric plate is kept between parallel plate capacitors, between plates of parallel plate capacitor, and where K is dielectric constant. Similarly, capacity with conducting plate will be equals to infinite, but this case has no significance because here the total circuit will just be acting as a simple continuous electric circuit. So storing of charge will not have a great significance in this case. So we will be using these formulas. Even the formula that we have done earlier also, when thickness is not equal to the total space, C is equal to epsilon naught A by D minus T plus T by K. So these are the three formulas which we will be using further to solve our numericals.